So thank you very much for the invitation. I'm here as a co-project manager from the RENERG project. RENERG means Renewable Energy in the Future Energy Systems, but also as a coordinator of the capacity area chemical energy converter in the SCCR efficient mobility. I think we have several common interests, so I would like to start with a short introduction of a SCCR efficient mobility and go then to the CO2 emissions law. I think this could be a game changer in future towards CO2 reduced mobility. And then show our ideas for stored excess energy as fuel for mobility and the RENERG project. So the SCCR mobility, the main target is to reduce the energy or CO2 emissions from a today's scenario to a new scenario with much lower CO2 emissions and energy consumption by a demand reduction, more efficient energy conversion processes, and fossil energy carrier substitution. The SCCR mobility is divided into 2 innovation fields and 5 capacity areas. So the innovation field A, components, devices and processes, includes 3 technical oriented capacity areas. One is electric mobility, second one is chemical energy converters, where fuel cell systems and internal combustion engines play a main role, and the third field is minimization of vehicle energy demand. The second innovation field is systems aspects of mobility, where the integration, operation and optimization of mobility systems, as well as integration assessment of mobility systems are our capacity areas. There are also some educational issues going on, so a Master of Advanced Studies in Efficient Mobility should start in 2017, and a joint summer school on batteries is planned together with SCCR heat and energy storage and SCCR mobility in July. Oh, it already happened, I see. We have 23 research groups and a lot of industrial partners. Now coming to the CO2 emissions, which is, in my point of view, the clear megatrend today in powertrain technology development. Not only in Europe and Switzerland, but worldwide, we have CO2 reduction regulations for passenger cars at the moment. We see here, for example, European path, but also India, USA, Canada, China, Mexico, South Korea, and so on. And even if the real-world CO2 emissions are somehow higher than this certification values, the main target of these regulations is to reduce the CO2 emissions of vehicles. And this is the only energy sector worldwide which has this type of law. And I think this is a similar impact. A similar impact is possible as 25 years ago with the exhaust emission regulations. We will now see a lot of new technology coming in passenger car, light-duty truck and heavy-duty truck market. And as Rolf Huber mentioned, I think also the competition between the different technologies is very important. Now, how is the situation in Switzerland? Here we see the gasoline and diesel fleet Europe, the so-called alternative fuels fleet in Europe, and in the Swiss fleet, all fuels. In Switzerland we have higher powered motor vehicles, larger motor vehicles, passenger cars, and therefore the CO2 emissions are significantly higher than in Europe. In 2015, we have for the first time a CO2 limit at 130 grams per kilometer, and today or last year the Swiss value was exceeded by 19 gram per kilometer. If we have in 2015 a similar non-compliance with the 130 target, this would cost the Swiss importer roughly 50 to 80 million Swiss francs only for this year. In 2020, the CO2 limit is reduced from 130 to 95 grams per kilometer, which will increase the penalties significantly if not the complete fleet is coming down with CO2 emissions. Now going to the energy situation. I would like to start with the new energy policy scenario from the Swiss Federal Office of Energy. There is not a clear mobility scenario or mobility energy scenario available, but nevertheless in some publications, for example the Prognos Studies 2012, there are some figures given for the mobility. So 2050 it is expected to have 40% electric vehicles, so plug-in vehicles, also plug-in hybrid vehicles, and 60% non-plug-in vehicles. It is not so clear defined which vehicle belongs to which category, but I think the simplest thing is if a vehicle has a plug-in cable, it belongs to this one, and if not, it belongs to this category. The mileage is also looked separately, and there is a overall or a average fuel consumption target mentioned. So 1 megajoule per kilometer, which is let's say 1/3 of the today's energy consumption of the whole passenger car fleet. This would correspond to 3.1 liter gasoline equivalent per 100 kilometers, but for real driving situation. Now, assuming a ratio between electric mobility and non-plug-in vehicles of 2 to 2.4, today we have roughly a factor of 3. We can calculate the target energetic consumption for electric mobility and for non-electric mobility. And of course this is the average target if this fleet would cover the whole fleet. If, for example, electric vehicles are mainly focused on small vehicles, the value should be lower and this a little bit higher. And now it is written in this Prognos study, if a CO2 target from 1.5 ton per person and year should be achieved, this non-electric vehicles have to be driven by 65% of renewable fuels. So this is a very tough issue. It is not possible to achieve this target with biogenic fuels, so we have to use synthetic fuels, so electricity-based fuels. And now, taking into account the whole story, we see that new powertrain technologies have to come. The vehicles have in totally be much more efficient than today, and we have to have renewable fuels, not only for a few vehicles, but for a large quantity of vehicles. And now the main question is, from where is this renewable energy coming? We have some unused sustainable biomass. This is stored solar energy. It is not so clear from how much of this energy is available, maybe 2 to 10 or 11 terawatt hours per year. And we expect to have some excess electricity in summer. This is a scenario from Swissgrid called Sun 2035. And here we have the calendar weeks and the energy production. We see yellow is the orange is the biomass, then blue is the water electricity. This is the pumped hydro energy, and yellow is the solar energy, photovoltaics. And this is the expected consumption for 2035. And we see in summer we have a lot of excess electricity, and while in winter we have a lack of energy. Sometimes we see some averaged values over the whole year, and I think this is a clear oversimplification of the system. Even to average the weekly energy production and consumption may be a oversimplification. So we have to know if it is a sunny and windy day or not, and if it is day or night. Nevertheless, we have quite a huge amount of excess electricity based on photovoltaics in summer, and it is expected that the similar situation will be in the southern part of Germany, in the northern part of Italy, and so on. So this electricity will be probably at quite a low price. And now the idea is to take some part of this electricity out of the electricity market and transform it to mobility. So we made some assumptions. So if we have, for example, 110 megawatt power to whatever facilities, this would be a 1 gigawatt mean power consumption. And if we take only this phase here, these are 21 weeks with 168 hours, so we have 3,500 operational hours. And this means 1 gigawatt times 3,500 hours is 3.5 terawatt hours excess electricity, I say, we use for the production of fuel for mobility. For example, hydrogen, for example, synthetic methane, and to substitute fossil fuels. Now, this is more or less the same picture. We have unused sustainable biomass. We have, let's say, maybe 5,000 summer hour hydropower, and we have in future fluctuating renewable excess electricity from photovoltaics. We are looking on 3 different paths. One is storage in grid batteries and use it for electric vehicles. The second issue, as Rolf Huber mentioned, is to produce hydrogen in electrolyzers and to use them for hydrogen vehicles. And the third part is to use hydrogen for a methanation of CO2 and to use the gas grid to operate gas vehicles. All these vehicles have different advantages and disadvantages. For example, electric vehicles have the highest efficiency, but it is possible to store maybe electricity only for hours. Hydrogen vehicles has a longer term storage possibility, but expensive infrastructure. Gas vehicles have the lowest price, but also the lowest efficiency. But we think that in the whole passenger car market, we need all these categories or segments to replace a significant amount of fossil fuels. If we only take 50% of the expected excess electricity in the Prognos study, we could run several 100,000 vehicles with a domestic CO2 neutral energy. Now coming to the RENERG project. Based on this, let's say, energetic situation or estimation, we applied for the RENERG project, and this project includes 5 work packages. The first work package is dealing with electrolysis, and here the main target is the evaluation and development of new catalysts. The project is led by Thomas Schmitz from PSI in cooperation with ETH Zurich and EPFL in Lausanne. The second work package is dealing with methanation. Methanation is quite a new discipline, and there are several open questions, and within this project or this work package, a specialty of methanation will be investigated. This is also done here at PSI. Third part, led by ETH Zurich and our lab, is dealing with combustion fundamentals. We think that especially in gas engines, there are also some open potentials, and one of the key problem on gas engines is the ignition. And therefore we are working on the ignition process for gas engines within this work package. And the fourth work package is dealing with hydrogen methane mixture as fuel. Hydrogen is very much improving the ignition behavior of gas engines, and so it could be very interesting to use hydrogen as a blending in natural gas or in synthetic methane as fuel. This fuel complies with very interesting requirements for future fuels, like very good ignitionability, very high octane number, and so on. And the fifth work package from ZHAW in Winterthur deals with market and grids. Economic aspects, we think that it is not possible only with putting the hardware together, and to operate the hardware in a good situation will make the whole story economically. We need also a very good situation within the market, the financial market and the electricity market. Now I will only go very quickly through the 5 work packages to show a little bit what is done. In the work package 1, electrolysis, there are 2 main activities going on. I will not go into detail because it's not my field of activities, and we have much better competencies here in the auditorium. But the main target is to improve or to develop novel catalysts, and I think it is very important if we go for synthetic fuel, electrolysis is the starting point, and this is a very interesting issue in this project. Second part is the methanation. So the main target is to optimization of the Sabatier process. And today we have an excess of hydrogen in the project, as I understand, and they are investigating here at PSI how this process can be optimized. Also, they are planning, or they are building a pilot scale and to run experiments to validate also models. In the third work package, combustion fundamentals, we see that ignition can lead to a very strong fluctuation of peak pressure in the cylinder of an internal combustion engine, and we think that an improvement of the ignition here could avoid this bad combustion process and to improve significantly the efficiency of the internal combustion engine. Therefore, we are looking at the ignition, spark ignition phase with a spectroscopic system to analyze how the chemical process is going on from a spark to early flame kernels. In the HCNG field testing, we are developing a fueling station which is able to blend hydrogen and natural gas, and we are also simulating how the temperature behavior at fueling or during fueling is if we take methane or hydrogen. And we already are operating 4 delivery vehicles together with Post, and we are monitoring these vehicles, and we see a shorter crank time of the engine. Blue is with only 2% hydrogen blending, while a conventional gas engine needs roughly double or twice the time to start when it has no hydrogen in the fuel. VP5 market and grid is dealing with this excess electricity. This also depends from the place where the power to gas facility is located, because we have a local and timely decoupling from the energy demand, and so it is important to know all the factors where power to gas or power to hydrogen facilities has to be installed. And also the whole market instruments are simulated to look how power to hydrogen or methane facilities can be operated. Now coming to the summary, I think the CO2 legislation is the key driver today for automotive powertrain development, and this may change the game. I think also we have seen this also, that new technologies which were maybe not economically feasible a few years ago become now a high interest. I think also that CO2 legislation is not something very risky or instable. We see a very robust legislation worldwide, and I hope that this will be the case also in the future. Energy turnaround means more fluctuating renewable energy, and I think to store energy and maybe to transfer it to a new market could be very interesting. We have to use mainly renewable electricity in summer without increasing the electricity demand too strongly in winter. This is possible with synthetic natural gas, for example. And the RENERG project aims to an improved understanding of the relevant technical and economic aspects linked to this synthetic hydrogen and methane production. On a long-term basis, we think that synthetic gases and liquid fuels would allow to substitute a large amount of fossil fuels. I would like to thank to the colleagues leading the individual work packages and to the funding agencies, Competence Center on Energy and Mobility from the ETH domain, Swiss Federal Office of Energy, Swiss Energy Research Fund, and for research fund from the gas industry. So thank you very much for your attention.